Good morning. This is really a pleasure to be here and to have the first talk after the nice talk before. Today we will speak about how to use deep learning in order to help food recognition for monitoring food intake. So why do you think it is important? If you go to the statistics, for example, in diabetic people, so diabetes is really a pandemic. Here we have 371 million people all over the world that have diabetes, and it is growing. That is only in 10 years, we will have 550 million people that have diabetes. And even if that is for these people, it is very important to provide them tools in order to improve their nutrition. If we think about obesity, obesity is also a very big problem for the world, for the civilization, for our planet. We have 10% of all the adult population is obese. And these people, just to show, for example, they used to spend 25% more in their health care, and they used to live 10 years less than the average person. So this is really a very important problem for all over the world. And the worst news is that this tendency is growing. And this is growing in USA, but it is also growing in Europe, in England, in Switzerland, even in Spain, where we have this so famous Mediterranean diet. In fact, in Spain, the children, they have the highest rate of obesity in Europe. Out of, we have the Mediterranean diet. So what happens here? So the point is that when we think about how to help people today in measuring the nutrition, in trying to make them more living healthier. So for the healthy habits, what we always reduce to the two main reasons. This is physical activities and diet. So for the physical activities, all of us, we have Fitbit, we have in our smartphone a lot of already installed apps, even if we are not aware, that are measuring, counting our steps. But what about nutrition? Is there any way to measure what people eat? So when professional people, dietitians, want to know how people eat, they ask them to fill in this food questionnaire. So they should try to write down here what they eat in the morning, midday, afternoon, etc. Do you know what is the difference between what they put in this paper and what is the reality? 35%. It was quantified. So because nutritionists saw that this is not the right way, they define it as food frequency questionnaires. And food frequency questionnaires is a very long questionnaire that asks questions like, how many boiled eggs did you eat this month? How many croissants with chocolate did you eat this month? Etc. Can we think about asking all the questions about all the food possible? So definitely this is not the right way. So let's just think about, and we are not the first that thought that this is important. And that's why there are different digital diaries that try to do this process easier. So we have today Spark People, Lose It, MyFitnessPal, Chronometer, Fat Secret, where you can write down all that you eat. The point is that we don't do this. We don't like to write down everything what we eat. And that's why it is not working at this moment, although it could be very helpful. And the idea is to help the people. So, how many of you have seen people that go to the restaurant and take the photo and take the smartphone and make a picture? Right? Several of them. And it is much easier to take a picture and then the algorithm behind to process this and then to construct automatically this diary. So this is our idea. So how to help to create automatically these diaries for food intake monitoring. Of course, this is not the first one, and there is also the alternative. So there are now some of the applications they are trying to do this, and they try to automate this process. Like for example, Lose It. They also say they are doing this completely automatically, applying food recognition algorithms. okay? But how many foods are they recognizing? How many foods are there? So according to the Wikipedia, this very well cited and consulted reference, we have 8,000 very basic food categories. But in general, we are speaking about 200,000 food categories. Okay, so is it possible really to do food recognition with 200,000 categories? Well, this is a challenge. And why is this a challenge? Because if we think about all kinds of food, as you see, this is not just recognizing if it is a pedestrian or it is a car. It is much more complicated. So, for example, can you say, what is this one? Food, yes. And what category is here and how many different foods will you have here? So it's really complicated, yeah? But anyway, we try to approach the problem. So if we try to summarize the problem is that the difficulties of the automatic food recognition is that we have a very high, very huge interclass variation. For example, all this is apple pie, also all of it is very different. And also we have very ambiguous definitions. So what is the class? Is it a pie? Is it an apple pie? It is an apple pie with cream? How many categories we should define? There are a lot of interclass similarities, different food. They can look very similar, like fried bread or steak. And there are a lot of mixed items in the same image. So this is really challenging problem. And then because the problem is very difficult, we need a huge data set in order to train. And the worst news is that this huge data set should be annotated. It should be supervised. So, do you know any powerful tool in order for data processing in order to address a very complicated problem with large amount of data? All of us, we read every day about deep learning. And indeed, this is really very powerful news. So, very powerful technology. If you go to Google Scholar, that is like today a reference for all of us in science, and look on which are the most influential papers last 2 years, you will see that from the first 7, 5 are on deep learning. And then we have also, or 4 in this case, 4 are in deep learning, and then we have 2 about health, especially on obesity, and we have some also about physics, etc., etc. Okay, so this is really challenging, it's really promising. And definitely today, without deep learning, we will not have all these successes where we speak when we see about drug discovery, about autonomous driving, about security and video surveillance, about media entertainment for video captioning, video search, etc., etc. So, and even with deep learning today, big companies are trying to help to the very global and important problems like climate and energy saving, etc. Now, how can we use this? That is another fact is that today deep learning is even better than humans in very different problems like object recognition, lip reading, high-end surveillance, facial recognition, object-based searches, license plate readers, and even go for breast tomosynthesis or for cancer lung diagnosis. Okay, so another, I like very much this example. So today deep learning are even good artists. So they are able to paint the same picture in different styles, in Van Gogh or Monet and Cézanne styles, etc. Even another example I like, this is the first art piece that has been created by deep learning, and it was sold by somebody, but by the authors, for this amount to somebody, to people that like art. So deep learning is at this moment in the hype cycle. Yeah, this is a very big expectation, and for solving really complicated problems. And this is not, this is very logical, because if we think about, if we see how science has been evolving, we see that in fact we are in the fourth phase of the science paradigms. That is, now today we all are in a stage where we have a lot of data, and also we have a lot of software, a lot of information knowledge, and also very good models. How to put this together, this is the challenge of our phase at this moment, So in order to do this, we need to think about how to put together data, resources, and models. And if we think about these three important pieces in order to do something meaningful, so which of the components we have already? So if we think about resources, so today we have very powerful GPUs that are able to process big amount of data. So they have ability to process 200 times, that is 2 orders bigger amount of information, and we are speaking just last 2 years. And also we can use GPUs in the cloud that is very helpful for many scientists. From point of view of data, we generated as much data as, that is last 2 years, we generated as much data as all the civilization before. So we are speaking about today about millions and millions of text and images and videos, etc. So today we have a lot of data that definitely are very important in order to address these difficult problems. Like, for example, today, every day, 103 million of spam emails are sent. Nobody will argue, right, about this. Okay, now how to use this information in order to train our algorithms. Okay, we are in this stage where our algorithms are able to manage that we should be able to manage big amount of data. That is, today our data set should have much bigger amount of objects to recognize and images in order to train our algorithms. Okay, today we have data sets that contain millions of images. We have the ImageNet with 14 million of images in total, with 1.5 million annotated images, but also we have thousands of images annotated for segmentation, for place recognition, for medical analysis, even for waste to detect in the wild, for even images and text in order to train how to dialogue and how to drive. Okay, we have a lot of information in this case, in the generic case, but what about food? Which are the food data sets we have at this moment? At this moment we have a few data sets that are public, but if you think about all these data sets, we are speaking about 150,000 images at most, and as 230 categories at most. So if we compare with other object recognition, where we have at least 1.5 million images annotated and 1,000 of categories to recognize, we see that we are very far. So on the other hand, what is the number of images and what is the number of categories we need in order to recognize? This is a good question. Okay, so if we try to make this simple calculus, we can see that for today, if we claim to go to 200,000 of images classes to recognize, we would need 280 million of images, and this should be annotated. So probably we are still not in this situation, but we should go forward. Anyway, so today we have a very powerful techniques, so we should work on this and we should try to address this problem. And so this is called deep learning, and deep learning have different models. One of them is the convolutional neural networks. So in the convolutional neural networks, we have a model that is constructed by some layers. So we have an image that is used as input, and then the last layer is used in order to classify which food we are speaking about. So the whole process of training convolutional neural networks is how to use a lot of annotated images in order to adjust these weights of the different layers, so that when I have a new image, the neuron that is corresponding to the food category, the right neuron is hired. This is this convolutional neural networks. In fact, one of the first began from 1998, but really the boost was from 2012 when ImageNet appeared. Today, there are a lot of different deep learning techniques. There are a lot of networks, and all of them, they have slightly different architectures, but in all of them, the big problem is how to train these millions of parameters that are inside the neural network. So you can see that here we have the different architectures of neural networks and their accuracy. So it is difficult to say which is the best one, but there are few candidates for this. Now, what makes the deep learning very popular? So on one hand, the promise here is the hope is because in all these different networks, in fact, the question is that we train this network. So we shouldn't decide on what the neural network should focus. So the algorithm is able to train us, the babies, as kids, when we show a lot of different examples. So the neural network is able to train what is the food in the image. Also, it is modular. So we mentioned there are different architectures we can construct, and it is easier to put another layer, to change layers, etc. And also, it is doing transfer learning, and this is really very interesting for the transfer learning. So what is transfer learning? Transfer learning is the ability to reuse knowledge from one domain to another, from one problem to another. So to try to explain it metaphorically, so maybe you have seen this movie where this lady, she has amnesia, so she forgets everything each night. So in the morning, she wakes up and she finds a unknown person in her bed, and she should know that this person is her husband, and she should fall in love in this day, and she should understand that she has a family, etc., etc. And during the night, all this disappears. So our algorithms before were very much amnesic. But now, with deep learning, we can reuse. We can reuse from a problem from one domain to another. And this is really interesting in this case. So depending on all these possibilities, we can speak about how to translate information from one domain to another, how to translate information between different tasks, and how to make the algorithm to self-learn. Different possibilities we have for the deep learning algorithms. So here, for example, we can see that one of the well-known and very basic is what to do when we speak about fine-tuning. So we train from one domain to recognize, for example, here food from images of food, and then we can reuse this model in order to recognize objects from real life, like cats. But also we can do in different way. We can have a model that is, we do the same, from the same image we have different questions, that is, we are solving different recognition problem from this. We can also use another model where we mix different domains, like for example images and text. Or we can also try to think as how to use this model in order to generalize this task, that is, if we have different tasks that could be interrelated, like for example using ontology where we put information from very different kinds and different subdomains and different problems on different tasks. So in our case, going back to the food, what we do is here we have an image and we can make different questions. So we can ask, what is the cuisine? This is one classification problem. What is the category? This is meat, another classification problem. What are the ingredients? Another classification problem. And what is the dish? Another classification problem. So we have a multitask learning in this case. So multitask learning is a kind of transfer learning that has shown that it's working very well because it allows to help the information we extract from one task to another one. And in our case, what we can do is have this multitask learning problem where we combine all different tasks from the same images, from the same domain, and try to see how they help each other. The point is that when we try to put all these different tasks, different recognition problems in the same model, how do we manage to control, to guide these different tasks? So, for example, when I ask the problem, what are the ingredients, definitely this will be much more difficult to say than, for example, if this is a food or not, or what is the cuisine, definitely. So, in this case, I should also try to guide or to restrict so that tasks that are more precise should have more priority in order to help to the other task, and tasks that are very imprecise, a lot of raw error, they should affect much less to the others because maybe we are worsening the problem. So for this we need to try to see what does this mean, what is this error in precision. And in this case we speak about uncertainty. So the idea is how to make these priorities, express them as uncertainty. So let's talk about uncertainty. This is the last issue. So when we speak about uncertainty in our model, so in fact what we want to know is when our model is giving an answer, we want not only to have an answer, but to know the confidence with which this answer is given. That is, imagine that a physician is using a deep learning algorithm in order to decide if a patient should be proceeded with surgery. So it is not the same if the deep learning says, okay, this is a cancer and you should proceed with surgery, 99% of confidence, then it is a cancer, but I'm 55%. Yeah, so in this case it is the same. So we need to express, we need to get this uncertainty about our models in order to decide how to make this transfer learning from task to task. And this is a kind in order to help not only deep learning to be considered as black boxes, because we try to also understand how this is reasoning. Okay, so what is uncertainty? Uncertainty comes from different aspects. For example, uncertainty is very proper to the algorithms just because of their kind of training. That is, for example, if I have these 8 classes and I train to my algorithm in order to recognize apples and strawberries, so what do you think it will be the answer when I put this image? Apple or strawberry, right? Because the algorithms are not intelligent enough in order to say, no, but this image is not one of all I was trained. Okay? This is one kind of uncertainty. This uncertainty is coming from the data. We speak here about aleatoric uncertainty. When we have, for example, different classes, some of these are with more errors and some of them are with less error. So our algorithm by default, they are not trained in order to say, okay, when you have this kind of classes, well, you should take into account that here we have much more error. And also another error is coming from the model. So if I have the same data but I use the different models, definitely the generalization error, the generalization capacity of my model will be very different. Okay, so all of this, that's why we are speaking about different kinds of uncertainty. Aleatoric when it is coming from the data, and epistemic when it is coming much more from the model. Okay. So in our case, what we do is we have the image, we define these weights that are weighting the different tasks, so that this weight depends on the uncertainty that is estimated from the data, from the aleatoric uncertainty. Okay, so in this way, what we do is our more precise tasks are affecting less, or are affecting more, are helping more to the other task, and vice versa. So in our case, we have our food ImageNet that we are constructing. This ImageNet is the biggest one at this moment. So we have at this moment ingredients and drinks and food and and cuisines, and also categories, and 600 in total food classes. Okay, so we are still far from 200,000, but it is more than what we have today in the public data. So if you have curiosity, you can go to www.logmeal.es and try to see. There are 100,000 food images where you can see how it is working. So for example, you see that in these cases, even in these images, we see that the dish is well recognized. Even the ingredients in this case were well recognized because it is quite coinciding with the ground truth in green. When it is not coinciding with the ground truth, it is in red. So definitely in these images, it is very difficult to recognize the ingredients. It is logical. And in this, for example, it is quite more easy to recognize. So for example, some of you will ask, how do you recognize ingredients that are not visible? Yeah, we don't have them in the image, but we have the multitask learning problem. So we know that when we have one recipe, one dish, we know which are the ingredients. So we use all this information together in order to help each other. Okay? So these are the results where we can see that our model, that is this multitask learning model, here we have the different possibility. I will not go into details, but the purple one is the best one, and that use uncertainty in order to help the problem to recognize better. So in this case, you see that we use the uncertainty not only to know which is the uncertainty of the final answer, but also to help in the training process. Okay? So some results, for example, here, you can see in this heat map, for example, you see these are the regions where our algorithms use it in order to decide that it is, for example, baked potato. It's going a little bit fast. Paprika, it is great. Pork stick, Brussels sprout, meatballs, mashed potatoes, pork steak here, and chicken, and green beans, and etc. Okay. Okay, and last, what we also are working at this moment is using this information in order to try to understand this whole cooking process. So the idea here is that even if you have cooking videos, that we have a lot of cooking videos in YouTube, out of here this is IP Kitchen, a very good public data set. So what we can do is here recognize the different foods in order to understand the whole cooking process. Okay, so conclusions. I would say that food image world bring us a huge amount of data in computer vision challenges and questions. It makes us redefine which are the data sets, which are the problems, which are the questions, which are the answers, which are the methodologies, the right methodologies, and the right technologies. And transfer learning is a good candidate to address this problem and to solve different sub-problems, as for example multitask learning, but this is of course not the only one. And uncertainty modeling is a hot topic at this moment with many open questions and challenges. And here we have an illustration how uncertainty modeling can help improve models and give more information than just the final answer. And here we can speak about epistemic and aleatoric uncertainty, a lot of interesting questions and very active area. And a huge impact of food analysis is expected from point of view of science, because we have really new and challenging problems, but also from real world applications, especially important for the society. And that's my talk. Thank you for your attention.
Thank you so much for your speech. I would like to know, did you try to solve some regression problem, for example, predict number of calories or something like that?
Okay.
Thank you.
Yeah. It's a good problem, good question. Okay, because we are working at this moment in three real problems. that is related to 3 European projects. And there, of course, the final question is this: how to estimate the final amount of calories. So the final amount of calories, it depends on not only on kind of food, depends on the amount, and depends on the way of preparation. Okay, so it's a long process. So at this moment, we are doing this approximately. That is, what we do is here we follow as the initial diaries we mentioned, where you say, okay, for this food, the individual dose is so much grams, so for each ingredient, and then we have a very good scientific and nutritional databases where you say 100 of carrots correspond to so much hydrocarbs, so much proteins, etc., etc. Okay, it is very difficult to have the absolute truth from the images. Yeah, but what we can do is from this part, what we follow is at least what is done until now. But the process, the whole process is what we recognize is the food, okay, and from the food we have the individual recipes, and from the individual recipes we translate them in nutritional composition. Okay, but definitely this is not absolutely true. That is, if people put butter or olive oil, they should say this. We cannot see this from the images. Okay.
Okay, so this is a main goal, but it is quite complex.
Yeah, it is. Yeah, it is.
Thank you for your presentation. And two questions. One is about artificially generating data, like salads, for instance. Salads is just a mix of different ingredients. Do you try that approach? And the second question is about recognition. You are talking about some CNN that recognize the categories, and a month ago there was an explanation what actually ResNet learns about the ImageNet, and they said that the base knowledge they gain is the textures rather than shapes. So that make possibly that is good for this task, but actually people usually differentiate different object by shape, but not the textures. What do you think about that?
Good. Going to the first question, yeah, definitely we are also working on synthesizing data, but not final results yet. It is not so easy, yeah, to synthesize here data. Definitely we are now working on GANs also, but it is complicated. That is, I cannot just get the carrot and put in another image. But definitely this is very important and very interesting question, and it makes a lot of sense in order to work on this. About the second question, that is, well, I'm not sure that the texture is not captured in our case, because in food there is a lot of texture. So but definitely it makes sense to look a little bit better. But I think that at the end it very much depends on the data. I understand that in general, I don't have the right statistic, but in the real world maybe we don't have some, that is the percentage of objects we have with texture and not texture. I don't know what it is, but in food, texture is very important. And I have the intuition that it is captured by the algorithms. Yeah, because otherwise, when you have this kind of rice, how do you separate the different kind of rice from other food? So texture is important, and food, and that shape here. In a lot of food, you have just a ball. So if you separate, if you discriminate rice from potato, it's based on texture and color, not on shape.
Thanks, Petya, for this lovely speech. I have been working in a project that is closing now that's about diets. My input data is the kind of food that people is eating, so Thank you very much for working on that, because we were working on surveys and on the declaration of the and inconsistencies in data so big that it's very difficult to work on that. So two things that I found in that project that I don't think if you found the same as we found or not. One is that we found that decomposition, the nutritional decomposition of prepared food changes according to the country. So roasted chicken is not the same nutritional decomposition in Spain that in United States. And this created a lot of problems in managing these issues. So one question is, did you find that as well? And second one is, you decided to approach the thing in a way of identifying every single ingredient on the dish, but we were following an approach about working with the entire prepared foods. And my question is, wouldn't it be easy to tag a dish like roasted chicken or, I don't know, vegetable soups, instead of trying to identify every single ingredient there?
Yes, in fact, this is a multitask learning. So one of that is we have the different tasks. One is the cuisine, another is the type. It is drink or food or sauce or some ingredient. Another one is the dish, and another one is the ingredients. So we have all these tasks, right? And from this, for the ingredients, what we have is on one hand, ingredients are coming from recipes, and this is what predetermined, and on the other one is coming from the images. But definitely we provide to the nutritionist the information about the food, yeah, and then the patient is confirming the food, then it is translated to the ingredients, yeah. So in fact, the nutritionist need to do this statistic to say, okay, this person is gluten oriented, yeah, because he likes pizza, pasta, etc. Or this person misses vegetables, or this person have very different food and diet. So definitely this is there, yeah.